The MCAT is going to ask a lot of questions about sound waves and light waves. And while there are some differences between sound and light waves, there are some characteristics that are going to be the same between all waves. A wave is simply an oscillation or vibration that travels through space, and in the process, it transfers energy. Generally speaking, there are two kinds of waves, longitudinal and transverse. The difference between a longitudinal and transverse wave lies in the difference between the direction of the oscillation or vibration of the wave and the direction the wave is traveling. For example, we frequently will draw light waves in this wavy S pattern like this. We draw a light wave in this fashion in order to show the wave is vibrating or oscillating in an up and down motion, similar to someone using a jump rope. However, the light particle is actually traveling from left to right, or along the x-axis. Sound waves, on the other hand, are an example of longitudinal waves, and longitudinal waves operate by shaking a medium back and forth along the same axis that the wave is traveling. Usually, when we draw sound waves, we show the vibrations going from left to right. At the same time, the wave is also traveling from left to right. One of the key differences between a longitudinal and a transverse wave is whether or not the wave requires a medium or a substance to travel through. Transverse waves, such as light, don't require a medium, meaning they can travel through the vacuum of space without a problem. Longitudinal waves, such as sound waves and earthquake waves, actually require a physical substance to shake back and forth in order for the wave to travel. That's why sound cannot exist in the vacuum of space. If you've ever seen a sci-fi movie where there's a big explosion and a big boom out in space, that loud sound didn't happen. It's because longitudinal waves require a medium or a physical substance to shake back and forth, or the wave simply does not exist. Whether we're talking about longitudinal or transverse waves, we frequently draw all of our waves in this wavy S-like pattern. And that's because this depiction allows us to clearly illustrate some of the key characteristics of a wave. The first characteristic is amplitude, which is simply a measurement of how tall the wave is. We're also concerned about wavelength, and that's how long the wave is. A full wavelength is going to touch the x-axis or the center of the wave 3 times, and it will cover one full peak and one full trough. So this would be my full wavelength. I could also draw my wavelength like this, and that still works because I'm still touching the x-axis 3 times and encompassing a full peak and a full trough. The difference between a peak, or a trough and a trough, that's called the wavelength, represented by this symbol here. The time that it takes for a wave to travel from peak to peak, or trough to trough, or one full wavelength, that's called the period. How often a peak or a trough passes in a second, that's called the frequency. The period and the frequency are inverses of each other. In other words, frequency is equal to 1 over the period. Likewise, the period is equal to 1 over the frequency. The MCAT will also ask about velocity, and velocity is equal to the frequency of the wave times its wavelength, or how long is the wave and how many waves pass by in a second. A lot of the characteristics of a wave have a human interpretation. For example, with sound, we interpret the amplitude with how loud or quiet the sound is. With light, we interpret the amplitude as how bright the light is. So a high amplitude is very bright, and a low amplitude is not bright. Likewise, a high amplitude of sound is very loud, and a low amplitude is very quiet. Frequency also has human interpretations. With sound, a lower frequency we interpret as a lower pitch. A higher frequency is a higher pitch. With light, we interpret frequency as color. To the human eye, a low frequency is interpreted as orange or red, while a higher frequency is interpreted as being more blue or purple in color. You'll notice that green is right in the middle of the visible spectrum. That's because the human eye is designed to see the color green the best. But not all animal eyes work this way. Many animal eyes actually see blue better than green, and others see red better than green. When multiple waves occupy the same space, you have what's called interference. And that interference can be either constructive or destructive. If the peaks and the troughs line up, we say that's in phase. And the result of two waves being in phase is the amplitudes magnify, In other words, the peaks get higher and the troughs get lower. When the peaks and the troughs don't match up, meaning a peak is lined up with a trough, the peaks and the trough end up canceling out. And the result is those peaks and troughs flatten out, sometimes completely. You may have heard about noise-canceling headphones, and those operate by intentionally creating waves that are out of phase. So as the sound wave comes into the headphones record that sound and then play it back a tiny fraction of a second later, replaying the exact same sound with the exact same frequency but slightly out of phase. The result is the peaks and the troughs cancel each other out, and you're left with a much flatter wave, which you interpret as a quieter sound. Here's a question about the velocity of a wave. So we're likely to use our equation that the velocity is equal to the frequency times the wavelength. In an ocean wave, the frequency is simply how often does a wave come ashore. In this case, it's 1 every 3 seconds. So 3 seconds is the period between the waves. Remember that the period is equal to 1 over the frequency. So if 3 is equal to 1 over frequency, that means the frequency must be equal to 1/3. The question also says the peaks are 14 meters apart. That's the wavelength. So to calculate the velocity, we simply say that velocity is equal to a frequency of 1/3 times a wavelength of 14 meters. Or the velocity is equal to 14/3, which we could estimate to be 4.5, or the wave has a velocity of 4.5 meters per second. Here's a question that's definitely set up to try and trick us. The temptation is to think that frequency and wavelength determine the velocity because we're familiar with the equation that the velocity is equal to the frequency times the wavelength. And while we can use frequency and wavelength to help us calculate the velocity, you should remember, however, the velocity of a wave is completely determined by the medium or the substance the wave is traveling through.